Hello everyone. Today I'm going to talk about the Poljak-Rodl function. And this function is motivated by Hedetniemi's conjecture, which is about the Cramaknum of the product of graphs. Suppose we have two graphs, T and H. The product, T and H, has the vertices, the pairs, such that pairs xy, such that x is the vertex of G and y is the vertex of H, and in which xy is adjacent to x prime, y prime, if and only if x is adjacent to x prime in G and y is adjacent to y prime in H. And Hedetniemi's conjecture is about the Cramaknum of this product graph. And this conjecture says that Hedetniemi's conjecture says for every graph G and H, the Cramaknum of the product is equal to the minimum of the Cramaknum of G and Cramaknum of H. And this conjecture was proposed in 1966 and was disproved. It has received a lot of attention for more than half a century, and it was proved in 2019 by Shitov, Russian mathematician, that the conjecture is not true. Okay? The conjecture is not true. The conjecture is false. Okay? It means there exists a graph G and the graph H such that the Cramaknum of the product is strictly less than the minimum of the two graphs. Okay, so Poljak-Rodl function. So what is that? This function is defined as follows: for an integer n, we let fn equals the minimum of the Cramaknum of G times H, such that the Cramaknum of G and the Cramaknum of H are both great or equal to n. Great or equal to n. Okay. And the Hedetniemi conjecture can be stated as Gauss' conjecture is that Fn equals n. Okay. So the minimum is always equal to the Cramaknum of the two graphs is always equal to the minimum, so therefore Fn equals n. And the Shitov proved that this is not true. Shitov proved that what he proved that is that Fn is strictly less than n. This is for large n. Without that, Fn is equal to n if n is less or equal to 4. Okay, that is no. But other than that, we don't know. We don't know if F5 equals 5. That we don't know. Okay. Right after Shitov proved his result, then we Tardif and I, Tardif and I, using his results, we proved that Fn is actually less or equal to n minus log n to the power 1 of 4. This is also for large n. Okay, for large n. And then a little bit later, her and Wigderson improved this result also in 2019. They proved that Fn is actually less or equal to 1 minus 10 to the minus 10, minus 9 to the to a. Okay, this is for logic and here. That will not right. Okay, so then what I proved recently is that using Shitov's result, we can prove the following improvement. It's a little bit stronger than that. So what I proved also at the end of 2019 is that Fn is less or equal to 1/2 plus omega 1n. Okay. So I'm going to prove this result today. So to prove this result, we're going to use Shitov's result, but we need a more technical statement of Shitov's result, more precise statement. So in the Shitov's proof, the main tool used there is the exponential graph, which is a standard tool used in the study of Hedetniemi conjecture, which was first used on a study of Hedetniemi conjecture by Norbert Sauer, who is my PhD supervisor. Exponential graph. Okay. So take a positive integer c and kcg. That's the, you can think of this is the kc is complete graph to the power of g. Okay. This graph has vertices, all these maps phi from Vg to C. Okay. Here C, we use C stands for this set 1, 2 up to C. Okay. So the vertices of this graph, we can think of each map is a coloring of the vertices of G by colors from C. So each map is a coloring of the vertices of G by colors from C. But this coloring is an arbitrary coloring. You don't need to be proper. Okay? And for two maps, phi is adjacent to cosine in this graph, if and only if for every age of G, and this phi x is different from cosine 1. So now this finishes the definition of the exponential graph. So two maps, two vertices of the graph adjacent if this is true. Okay, we're going to use this graph. So we need to know a little bit more about this graph. So one observation is that if the image of phi is disjoint from the image of cosine, then phi is adjacent to cosine. If you take two maps from here, if their image are disjoint, then they are adjacent. Right? This is trivial because if their image is disjoint, then of course for any age, phi x is different from cosine 1. Okay? And there's one particular family of maps that are important, that are the constant maps. Okay, so for color I in C, we that GI be the map, which is constant map with the image of GI equals I. That means it colors all the vertices of G by the same color I. Then this set, see GI I belongs to C, induces a clique, right? Induces C clique in this graph. Okay? Because for any I is different from Gi, the image of Gi and the Gi are disjoint, so they are adjacent, so therefore it induces clique. In particular, this graph has Cronach number at least C. Right? For any, so maybe I write it down. Okay, so for any graph G, for any C, this Cronach number at least C. Another observation is that for any graph G, for any integer C, if you look at the product of this graph, G times KCG, this is C variable, and this is the Cronach number is less or equal to C. Why is that? Because I can just simply give a easy coloring. So you color this, you take a vertex from G and take a vertex from this exponential graph, and this pair form a vertex of the product graph, and define this is to be defined V. And this is a proper coloring of this product graph. So so this product graph is always C colorable. Okay? And actually, Hedetniemi's conjecture is equivalent. Conjecture is equivalent to the following statement. So that is, if the Cronach number of a graph G is bigger than C, then the Cronach number of KCG is equal to C. Okay. So as we said, this exponential graph, the Cronach number is at least C because it contains a C clique. Okay. So if this is not true, what does it mean? It means we have a graph, the Cronach number is bigger than C, and the Cronach number of the exponential graph is also bigger than C. But this observation, the product has Cronach number at most C. So therefore, the product graph has Cronach number strictly less than the minimum of these two graphs. So that therefore the Hill's conjecture fails. So the other direction, so this means this direction is true. The other direction is also true, but we don't need that. Okay. So that means to disprove Hedetniemi's conjecture, what do we need to do? We need to find the graph G and find the integer C, so that this is true. The Cronach number of this graph is bigger than C, and the Cronach number of the exponential graph is also bigger than C. Okay? So that is what Shitov did. And actually, we need a more precise statement of more technical results. What details of what are the graphs constructed in here? What is the graph G? Okay, so we state this theorem here. The theorem of Shitov, this is what Shitov proved, is that assume G is a graph. G is a graph with p vertices, and with girth at least 6, and with independence number is bounded by p divided by 4.1. So this is graph. Such a graph exists. That is in almost any graph theory textbook. It's a theorem proved by Eldish that there are graphs of ultra-large Cronach number, ultra-large girth. So in that proof, this is proof. This is easier than that one. It's a consequence of the proof. Okay, so we have such a graph. Then Q be any integer which is bigger than, greater or equal to 2 to the p minus 1 times p squared, and that C equals 4Q plus 2. Then the following is true. Then the Cramér number of G. Next co-graph product with Q is bigger than C, and the Cramér number of KC, G, K, Q is also bigger than C. So this graph, this is the this graph is obtained from G by blow up each vertex of G, each V in VG into a C clique, Q clique. Okay, replace each vertex by a copy of KQ. So this is the next co-graph product of these two graphs. Okay, so of course, as we said, once we prove this, then the Hedetniemi conjecture is disproved because you have two graphs. Each of them has Cramér number bigger than C, and the product has Cramér number at most C. Okay, so we're going to use this theorem to prove our result. So what are we going to do? It's also a result similar to this, a technical result similar to this. So let's write down this theorem. So this is what I proved recently by using Shitov's result. So assume G is a graph. Assume G is a graph. Assume maybe it's first state D is integer. Assume D is integer. Assume D is an integer which is at least 2. G is a graph with vertices, p vertices, curves at least 6, and the independence number which is less or equal to p divided by 8.2 d. Okay. So this is similar to this one, except that the independence number is even smaller. And also this existence of this is the same thing proved by Elvish using probability argument. Okay, then that Q be any integer which is greater or equal to 2 to the p minus 1 to the q p squared, and C equals 4Q plus 2. The conclusion is that the Cramér number of GKQ is greater or equal to 2DC minus 2C plus 2, and the Cramér number of KDC GKQ is also greater or equal to 2DC minus 2C plus 2. So this is the conclusion. Okay. So this assumption is the same, except the independence number is even smaller. Okay, so we're going to use, this is proved by Shitov, we're going to use Shitov's result to prove this result. Now first we say, what is the consequence of this result to the Poljak-Rodl function? If this is proved, if this is true, then what do we have? We have F2CD minus 2C plus 2 is less or equal to CD, right? Because we have two graphs, it's Cramér number this big, and the product is Cramér number DC, at the most DC. So therefore, this is true. And from this, if we let d goes to infinity, d is an arbitrary integer, we can let d go to infinity. D goes to infinity, and then you look at f2cd minus 2c plus 2 divided by 2cd minus 2c plus 2. So if d goes to infinity and c also goes to infinity, right? Because this this p, this number of vertices depends on d, because we want the graph as independence number which is related to d. Okay? If d is big, then p has to be big. But anyway, so you can easily say that this is because this is less or equal to d goes to infinity. On the top is cd, and 2cd minus 2c plus 2, and this is 1/2. This is 1/2. So this implies that the lower limit, when n goes to infinity, fn of n is less or equal to 1/2. By using the monotonicity of this function fn, and with a little bit more careful argument, we can actually prove the upper limit is also bounded by 1/2. So therefore, this fn is, so this means fn is less or equal to half n plus some error term. Okay, so now we're going to prove. So once this is proved, we have this constant, this constant. So this is the result we're aiming at, and so what remains to prove is 0. We need to prove this 0. So let's prove this 0. So we need to prove the chromatic number of this is bigger than that. That is trivial. So the chromatic number of G, K, Q, and this is greater or equal to the number of vertices. This G has P vertices, and each vertex is blown up into KQ, so the total number is P times Q, divided by the independence number of this graph, right? Because this is the maximum size of independent set, so each color class contains at most this many vertices, and therefore you need at least that many colors to color the graph. But it's easy to say that the independence number of this graph is the same as the independence number of G. Blowing up each vertex into K does not increase the independence number. So therefore, this independence number is less or equal to this. Right? So therefore, this is greater or equal to P over Q times this number, that is P over 8.2D. This is 8.2D times Q. And this is greater or equal to 2CD, because 8.2 times Q is bigger than 2C. Right? C is 4Q plus 2 is less than 4.1Q. Q is huge number. Q is something like this. And so this is greater or equal, actually much greater than 2CD. 2CD, of course, is, we just need this to be greater or equal to 2CD minus 2C plus 2. So this is certainly true. Okay. So now we need to prove this. Okay, to prove the next result, we assume phi is a CD plus T coloring of KCD GKQ. Okay, so we know this this graph, the chromatic number is at least CD because it contains a creep of size CD. So therefore it is, so phi is a proper coloring. It's proper, it needs at least CD colors, but maybe more. So assume that phi is a CD plus T coloring of this graph. We will show that T has to be big. We will show that if you have such a proper coloring, show that T is great or equal to CD minus 2C plus 2. If we have proved this, then the chromatic number is at least 2CD, CD plus D is the 2CD minus 2C plus 2. Okay, so that's what we're going to do. Okay, so let's see. First erase this part. So when we assume that for each I, for I belongs to CD, this color of this constant map, this is the constant map in this exponential graph, which colors every vertex here by color I. So we can assume this is colored by I, because this is GI. When I goes run through the CD, it induces a creep of size CD. So each of them has to be colored by a distinct color. Without laws of generality, we assume that this is colored by CI, colored by I. Now, the color set, when they color, the color set is CD plus T, which is 1, 2 up to CD plus T. Okay. So now this clique used colors 1D to CD. Okay. Then we S be the color which is not used by this clique, be CD plus 1 up to CD plus T. So S contains T colors. Now one observation is that for every phi belongs to this CD, GKQ, every map, you look at the color. So phi, this is a proper coloring of this graph. And what is the color of this map? This must belong to the image of phi union S. Because if I is not here, why is that? Say if I is not in this set, then phi is adjacent to GI, right? Because GI is colored by I, so phi cannot be colored by GI. So therefore the color has to be in here. Okay, now take say for a C subset, A of this set CD, with that HA be the subgraph, with the HA be the subgraph of this exponential graph, okay, say GKQ, induced produced by those maps with whose image is contained in A. Okay. So this is a subset of vertices of this graph. Sorry, this is not C, this is CD. Okay. Okay. So this subgraph, an observation. So this HA is isomorphic to this graph, to KCGKQ. Okay. So why is that? Say, what is HA? HA are the vertices of all the maps that color the vertices of this graph by colors from A, and A is of size C, and this is also color the vertices of this graph by a set of a set of size C. So therefore they are isomorphic. Okay? They are isomorphic. But by Shitov theorem, okay, the Shitov theorem so what we have is that this graph has chromatic number bigger than C. Right? Has chromatic number bigger than, therefore this one has chromatic number bigger than C. So this HA has chromatic number bigger than C. Okay, so now phi is this phi is a proper covering of the whole graph, and therefore phi is a proper covering of this graph. And the chromatic numbers, this graph is bigger than C, so phi used at least T+1 colors. C colors is not enough to color this graph. What are those colors? So those colors has to be contained in this set, in the image of those maps, union S. And the image of those set is A, right? They're contained in A. So therefore, let's write it. So this is, we observed it before, and we know, so we look at the color, they look at the color of vertices of HA. What are the colors? The colors has to be, each map in here, the color has to be in the image of phi. For any phi here, the image of phi is A. It's contained in A. Okay? And so this is contained in A union S. But it cannot be contained in A because A has only C colors and the chromatic number is bigger than C. So therefore, this phi HA intersection S is not empty. It must use at least one color from S. Okay? So with that, this is a subset of this set, with that tau A be an arbitrary color, be an arbitrary color in this set in phi HA intersection S. Now, okay, then for if A is disjoint from B, implies that tau A is different from tau B, right? Because say A and B are both C subset. A and B are both C subset. A, B are C subsets of CD. Okay. Because the maps in HA and the maps in HB, they have disjoint image set, and therefore they are adjacent, right? maps with disjoint images that are adjacent, so they cannot get the same color. Tau A, tau B has to be different. This means what? This means that tau is so this means that tau is a proper coloring. How many colors used? Use T colors, right? The colors are from this set from S. S is T colors. It's a proper T coloring of this Kneser graph. LKG CDC. Okay. What is Kneser graph? That's a well-known family of classical graphs, so let's define it. So Kneser graph G has two parameters and D. The vertices are D subsets of this N set, and in which A, B are adjacent if and only if A and B are disjoint. Okay, so if you take any two D subsets, this A, B are elements of this vertices of this graph, they're D subsets. Take any two D subsets, if they're disjoint, then they are adjacent in this Kneser graph. Okay, so it is a classical result of Lovász, which determine the Cramér number of Kneser graphs. So the results by Lovász. I forgot the name here. So this says the Cramér number of Kneser graph ND is equal to n minus 2d plus 2, and plug in this here. So therefore, T is greater or equal to the Cramér number of the Kneser graph with parameter CDC, which is CD minus 2C plus 2. Okay, so this finished the proof. We just need to prove that. We need to prove that T is greater than CD minus 2C plus 2. This finishes the proof of this theorem.